Okay, so let's show that we get a wave equation from Maxwell's equations in regions where there is no current, so the current density is 0, and there's no charge, so that's the charge density. And we're going to use the differential versions of the equations, so we're just going to motivate what this looks like, but we can follow it up to a certain point. So we know that the divergence of the electric field is equal to 0, right? Gauss's law for electric fields. The divergence of the magnetic field is the same, right? That seems to always be true. This is true because of this. The curl of the electric field is related to the time changing magnetic field, and the curl of the magnetic field, sorry, let me pull this down. The curl of the magnetic field is related to the time changing electric field up to some constant or combination of constants. So now let's combine these equations. So let's imagine evaluating the curl. Now this is a kind of derivative around in sort of the circular direction, whereas this is a kind of derivative in the radial direction. So that let's do the curl of the electric field. So by this equation, this is right. So the curl is a derivative in space, sort of around, and this is a derivative in time. So when we take the curl of this, we have to take the curl of this, but we can replace space and time. So we don't have to write this as minus the curl of dB by dt. We can just do minus d by dt. The correct way to say this is that they commute. You can do one or the other first. You'll get the same answer. So this becomes d by dt times the curl of the magnetic field. But we can, via this equation, relate that into the electric field. And so what we get is that we have minus d by dt times mu naught epsilon naught dE by dt, which is minus mu naught epsilon naught, second derivative of the electric field in time. So now let's assume, for simplicity, to get a sense of this, that E field is in the y direction. Then this curl of the curl actually reduces to something that's just related to x. So it's x derivative, so it turns out to be second derivative of E in x. And that, of course, has to be equal to this, so it's minus mu naught epsilon naught, two derivatives in time of E. We can just get rid of the minus sign, right? So we can just, there's a minus here and a minus here, we can get rid of that. And we notice that that's a wave equation. And we can also notice that this is 1 over the speed squared. So mu naught epsilon naught is 1 over the speed squared. So the speed, this just comes out of Maxwell's equations. The speed is 1 over mu naught epsilon naught square root. Remember where these constants came from. They were just the results of our experiments. And lo and behold, it comes out that this is the speed of light. Okay, we just get that from these equations. And so the solution to this is something like some amplitude for the electric field, say cosine of kx minus omega t plus phi. I don't need a square bracket. J hat, right? Now let's notice that the curl of the electric field, now we don't know exactly what that means. It's a kind of derivative around that actually turns, we get a vector as a result of that, and that vector is perpendicular to this one. So this equation tells us that these two vectors, E and B, are perpendicular to each other. But we can do the exact same thing with the magnetic field. The curl of B is equal to mu naught epsilon naught d by dt of the curl of E. Right, because the curl of B is related to d by dt, and so we want to take the curl of that, and so we get this. We'll do the d by dt afterwards, just like we did it there, and that gives us mu naught epsilon naught d by dt of minus dB by dt, right? Because the curl of E is related to the time derivative of B, so we can bring it back in terms of B only, right? So we're just trying to write these two equations here all in terms of E, spatial derivatives of E related to time derivatives of E, here spatial derivatives of B related to time derivatives of B. And so we end up with minus mu naught epsilon naught, two derivatives of B in time. And so this is, so B can be perpendicular, so B has to be perpendicular by this equation to E, so B is in Z direction. So two derivatives of B in X equals, I'll just put in the 1 over the C squared, two derivatives of B in time, that's a wave equation, and the solution, of course, is similar to what we saw there. This B naught is actually related to this E naught by the speed of light times the cosine of kx minus omega t plus phi k hat. So notice that the electric field is perpendicular to the magnetic field, right? That's implied by these two equations, because the curl, we don't know this mathematically, but we're just stating that fact. We would have to look at the curl expression to note, to see how the curl of a vector produces a vector that's perpendicular to this vector. So E and B are perpendicular, but they're also perpendicular to the direction of wave propagation. Okay, so the electric field is pointing one way, the magnetic field is pointing the other, and the whole thing is traveling in a direction that's perpendicular to both of those.